All right, today we're going to go into solutions is our new unit, and we're going to do a lot of stuff with it. So solutions are really, really important as far as what we deal with in chemistry. So let's begin. Let's go forward. Come on. It's having a hard time. It doesn't like me. Okay. Some definitions that we need to know. Okay, a solution is a mixture of two or more substances in a single phase. Okay, so they're in the same phase. One constituent is usually regarded as a solvent and the other one as a solute. The solvent dissolves the solute. So if I make salt water, the salt is the solute and the water is a solvent. Yes? If you've got a blank that you need to fill in. So make sure you're following as you go. Like missing part of it, of the slide. Yeah, I try and help you. We'll get there, hopefully. Whoa, 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 back. Back. Will you take it back for me, please? 2 slides. Okay, so we're going to go forward here. All right, so parts of a solution. We can have lots of different things. When people think of solution, that's what they think of first, is like salt water. But we can have lots of different things. We could have a solid and a solid. That's like silver and gold. We could have a solid and liquid like salt and water. We could have a gas and a solid like hydrogen and palladium. We could have liquid and liquid like alcohol and water. We could have a gas and a liquid like oxygen and water. We can have a gas and a gas like as in air. Air is a mixture. As a solution. So solid again, that's the part that's being dissolved. Solvent is the thing that's doing the dissolving. You have to have a solute and a solvent to have a solution. Yes? Yes?
What's the abbreviation for it?
Little P. Good question. You think it's PD, but I'm... No, PD. PD. Okay? All right, some definitions, other things. What do you need? I got it. The ones down here don't work, but the ones over here do. All right, we ready?
2 more seconds. Okay, you're good.
Okay, so some other definitions that we need to know. Solutions can be either classified as saturated or unsaturated. A saturated solution contains a maximum that we can have at that temperature. So I've dissolved as much as I can at that temperature. And unsaturated means I could still dissolve more if I wanted to. So in other words, when I make Kool-Aid, is it saturated or unsaturated with sugar? Unsaturated, unless you're like the little kids that like to keep putting sugar in. Okay? And you end up with a syrup, right? Okay. Now, this one right here is just to sort of help you. We have some unsaturated and unsaturated fats. Probably you've heard of trans fats and things that are unsaturated versus things that are saturated. Cis fats are actually good for our body. Trans fats are not. Because our body needs to have this opening on a cis fat so that it can break it up, like on the oleic acid. But on stearic acid, you can see it's all straight. It's really hard for our body to get in there and break that chain because there's so many little hydrogens poking out and there's no opening for them. Okay? Some other definitions that we need. Supersaturated. Have any of you ever had or gone hunting or gone camping and you have these reusable hot pad things that you can use and they're clear and they're liquid and then you move a little metal thing inside and then it turns solid and it gives off heat? Okay, if you haven't done that, basically that inside that solution is a supersaturated sodium acetate, which is just baking soda and vinegar mixed. So you can actually make it at home. If you take about 1 liter of vinegar and you put in about a teaspoon to a tablespoon of baking soda and let it sort of bubble up and then heat it until you get a nice little thin skin on it, and then put it in a clean glass. Let it cool, and then you can take and actually pour that liquid and it'll make a column. It's really cool. So If you choose to do that and take a picture of it and bring it back, I'll give you 50 points extra credit. Okay? Just know it's stinky. Okay? Just know it's stinky. Next term. Oh, I know. Okay, supersaturated solutions are only temporary and usually only accomplished in one of two ways. Warm the solvent and then add more stuff to it and then cool it down. Or evaporate off some of the solvent by just letting it sit there and then be careful so nothing solidifies. So those are the two ways. This is the thing I was talking about earlier, the reheater. That's saturated sodium acetate. And it makes a heat pack.
Can you go back to 2?
2.
Yeah, I didn't get so bad.
Evaporate.
Warm
Warm and evaporate. Okay, and that's just an application of supersaturated ionic compounds. So this is what happens when you dissolve salt in water. Okay, when you dissolve anything in water, it starts as a compound, just like we did today in the quiz. But instead of staying as a compound, when it hits water, it becomes its ions. So remember we had the part where we had to figure out how many ions? So this one right here would make how many ions? 2. Okay, and you're going to be able to do that. Now, I have to remind even AP and honors, this little AQ here means aqueous or dissolved in water. It's a cute little ion. Anytime you have a charge, you need to put AQ because it's a cute little ion. It's dissolved in water, okay? All right, so aqueous solutions. How do we know ions are present in solutions? The solution, this is sort of a wrap. It's not really anything you fill in here. Okay, the solutions, they're called electrolytes. So when we have our solid and it dissolves into our ions, how many would we get ion-wise here? 3. We get 3 because we get 2 Cls and 1 Cu. So we get 3. So when they're dissolved, they're called electrolytes. You ever heard of an electrolyte? You ever drank Gatorade? Ever drank Powerade? They're good because they have got tons of electrolytes. They got salt in them. Okay? Electrolytes help our body's nerves to connect and talk to each other. So we have to have electrolytes to live. Okay? Strong electrolytes are ones that totally go into their ions. There's some that don't like to dissociate in water, and so they only partly go into ions. But the ones that have strong electrolytes are the ones that totally dissociate.
How can you tell which one's completely separated?
See this little thing here? You put it in, and if you get a bright light, it's an electrode, you got lots of electrolytes. If it's a dim light, not so much. So it's sort of fun. Okay, so we're going to call it, if they don't conduct electrolytes, like ethanol when it hits water, doesn't separate. Okay, so you ever put gas in water or oil in water, it doesn't separate, doesn't go to ions. Because of that, it's just water that's in there, and it doesn't conduct really well if you do it with distilled water. Those are called non-electrolytes. So those are things like sugar and ethanol and ethylene glycol. Those are things that are non-electrolytes. Now, you don't have to write right on the slide itself. If you want to write above or below it, that's great. Okay? All right? Okay, so it's time to play everyone's favorite game show, electrolyte or non-electrolyte. Electrolyte or non-electrolyte? Non-electrolyte. Yay, okay. What about this one? Because it's a sugar. If it's a sugar, anything that starts with a carbon or has carbon stuff, that's a big hint. They won't separate. Okay? Salt. Yes or no? Electrolyte. Good. Okay, next one. Octane. Good. Not. Next one. Good job. Okay. Next one. Yes, it's an electrolyte. It goes to the ions. What about the next one? Here's a tricky. No. Okay, the reason why if they're close together on the periodic table, it's a covalent bond. Covalent bonds don't give us ions. Okay? Yes?
Okay, when you say like on sucrose,
Mm-hmm.
when you say it doesn't separate, what do you mean by that?
It doesn't go to ions. It just is one little clump in there. Stays as one look up. Sugar still
Oh, I see.
looks like it dissolves, but it just is surrounded by
If
water.
you were to add enough sugar, you would be able to see it eventually,
Oh yeah.
and it doesn't dissolve. Is
Not-
that what you're saying?
It does it's surrounded by water molecules, so it looks like it dissolves, but it really doesn't.
So the ones that do separate, is that what happens?
They just go into their ions. Yeah, they just fall apart in their ions, and there's now ions in there.
So in the water we drink, how many other ions other than H2O?
Oh, you got lots of ions in there. You usually have some calcium and some iron and some whatever's in the pipes. Yeah, they put fluoride in. Okay. All right, let's go on. So electrolytes in the body. This is where Gatorade comes in. They carry messages. They're important that way. They maintain cellular function and help us maintain the things that we need. You could make your own by adding about that much sugar and some salt and squash. Yeah, that does sound exciting, huh? Okay, now this is where we start really getting into the stuff that we need. Concentration of a solid. The amount of solid in a solution is given by concentration. There's several different ways we can do concentration. The one we use in lab the most is molarity. And I do a little ditty to help me remember because there's another one that sounds really close to this one. So this is how I remember it. It sounds silly, but it works. Molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Okay? Molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. Now you guys do it with me. Ready? Molarity, molitery, molarity, molitery, molarity, molitery, moles per liter. You got to remember that. It's capital M. Okay, there's another one coming that sounds really close to it. So you got to remember that, okay? Moles over liters. Pretty easy, right? Plug it in, plug and chug. Okay, so basically we have to put the amount of mass that we weigh out that would be equal to a mole into what we call a volumetric flask first, and then dilute it up to 1 liter. Okay? So if I try to put the water in first and then put the salt in after, I would actually end up with this much excess water. So I have to put the salt in first and then dissolve it up. Okay, so here's a problem. Let's try this. I want you to try and write down. I think I left you some room. Dissolve 5 grams of nickel 2 chloride hexahydrate. Remember that? Hexahydrate. In enough water to make 250 milliliters of solution. Calculate the molarity. Molarity was moles per liter. So I got to change what to moles? The grams. Okay, so I'm going to change the grams to moles. So I'm going to calculate how many moles of this I've got. So I'm going to take this, I'm going to add up nickel, 2 chlorines, 12 hydrogens, and 6 oxygens. And that's this mass right here. Okay? Times the 3, I got moles. What was the other thing I needed? Moles per liter. I've got milliliters. So I need to calculate the milliliters into liters, which is just dividing it by 1,000, right? So I get 0.25. Take my moles, divide it by my liters, I've got molarity. Now in molarity, we also usually add in, I hope I can write in here, we'll see. We usually add in the nickel chloride dot 6 H2O after, okay? Because we want to know molarity of what, right? We want to know molarity of what?
So wait, how did you get the molarity?
Took my moles, right here, that I just calculated, and then I divided it by my liters.
Oh.
So I took this one up here, divided it by 1,000, and that gave me 0.250.
So you
If they don't give it to me in liters, I need to have it in liters. Moles per liter. Yeah. Okay? All right. So we write this shorthand like this. So brackets around something, that means molarity. So I can say this in brackets is this.
and the M is moles?
Molarity. Molarity. Capital M is molarity. Okay?
So why put the brackets around if it's just fixing molarity?
You don't have to have the M here then. Okay? All right, ready to move on?
Rewrite it in the shorthand.
Mm-hmm. Okay, any others? We ready? Not quite ready? Okay, going forward. Using molarity. What mass of oxalic acid, which is H2C2O4, is required to make 250 milliliters of 0.005 molar solution? Now this is what we usually do in lab when we're making stuff up. How much do I have to weigh out to make the solution that I need, right? Okay, so we're still going to use the molarity equation, but we're going to rearrange it. So we had molarity, moliter, moles per liter, right? So we're going to rearrange it so it's moles is equal to molarity times volume. All we did was rearrange it, same equation, still M is moles divided by liters, right? I just rearranged it. Everybody okay? All right. So step 1, change the milliliters to liters because it won't cancel out otherwise. So again, this is going to make it 0.250 liters, right? Because I divide it by 1,000. All right. Then we're going to put it in, just calculate it. Once I've got moles, I still don't know how much to weigh out, so I got to change moles to grams. We've done that 1,000 times. Okay? And this is the mass of the C2H2O4 down here. Oh, sorry, I got it in backwards order. Let's try it again. H2C2O4.
Are you getting 0.05 moles per liter?
0.05 moles per liter is right here. Okay? So I just times it. This is given, this I just changed, and it's basically given. Once I've got the moles, then I just look at the mass of 2 hydrogens, 2 carbons, 4 oxygens, and I times it by the moles, because that mass is moles per gram. And the moles will cancel, and I'll end up with this. I still should probably write over here, which I didn't in the PowerPoint, grams of what, right? Grams of what? It's just like from the mole map. So once I get moles, I just use the mole map and go to grams. Okay? We all right? Going forward. Okay, learning check. I want you to try and do it on your own. Try and figure out what you would do. Okay, how many grams? So we're looking at NaOH. I want you to figure out this problem, and then I want you to choose one of these, 1, 2, or 3, and we're going to have a poll here in just a second. Okay, so I converted this to liters, so you got 0.4 liters. And you're going to take this now and times it by it, and that will give you 1.2 moles. And then you just take that 1.2 moles, and in 1 mole, there's about 40, right? And that's how you get the 48. I didn't round here. I just added quickly. Sodium's about 23, oxygen's about 16, hydrogen's about 1. If you have a calculator, I would do the exact to 5. About 23 here plus 16 plus 1. Okay. That was just me quickly rounding and adding so you could sort of see how to do it. When you do it on your paper, you want to add to the exact number so you're not off. Okay? Everybody understand how we got this? Feel okay? All right. Now, there are other concentration units. In an ideal solution where one of the properties depend on the concentration of a solute, we need the concentration units to tell us how many particles are dissolved. The unit molarity does not do this, so we have to have a different one. Remember I told you I gave it a little ditty, molarity, moliter, molarity, moliter, molarity, moliter, moles per liter. Now we're going to learn one that sounds really close to it. I wish they would have chosen a different name, but I wasn't alive back then, so I didn't have a choice. So just know that we're going to work with something else that's really close, but it does different things. So there's actually 2 others. The first one is molality, and it's an italicized M. It's actually, I do that for the italicized M. Let's go back. Whoops. Forward. It's molality. You have to do it different because this one right here looks like, oh my gosh. Try again. Okay, that one right there looks like meter. And so you got to do it a little bit. I just put this little curly Q right here so I know it's molality. Okay, it's supposed to be an italicized lowercase m. Now, yeah, that's why I do that little curly, so I know which one it is. And it's a lowercase. Now, molality is moles per kilogram. So moles of solute per kilograms of solvent. Okay? Moles of solute, so the things you're going to dissolve, divided by kilograms of solvent, not solution. Solvent's what you're dissolving. What's doing the dissolving? So H2O would be a solvent if I'm trying to do, right. Okay, so you get that? Now the way I remember this is when I say it, I sort of overemphasize. Molality sounds fat. So it needs the kilograms. That's how I remember it. I know it's silly, little mind tricks, but that's the only way I could remember the difference. Okay, if it works for you, great. If it doesn't, try and find something else. Okay, the other thing that we worry about is percent by mass. And they often report air quality and water quality in percent by mass. And percent by mass is just grams of solute divided by grams of solution, times by some number. Now, percent would be times by 100. So it's just like finding your percent on a test. So here's the total amount. Here's what I got. This divided by total amount times 100 gives me my percent. They call that pph, parts per 100. Okay, instead of percent, they get all technical. Okay, it's parts per 100. Okay? Which is percent. Okay. But they also, going forward, come on. It's like it's stuck in around. We also have parts per million. It's the same thing, only instead of timesing by 100, I times by 10 to the 6th. And guess what? They also have ppb, and guess what you times by?
Billion.
10 to the 9, which is a billion. Okay, so ppm, ppb, pph, they'll all be on the CRT. You need to know them. But just remember, parts per, that's just like percent. Only it's just telling me what to times it by. Okay? All right, pretty easy. All right, so we're going to calculate, I just thought this is an awesome, cool picture because this is ethylene glycol. That's what it looks like, the structure. Okay, so we're going to use 1 mole of that, which is 62.1 grams, and 250 grams of water. And we need to calculate the molality and the percent by mass. Okay, molality and percent by mass. So I'm going to go to the next page here, say that's the same thing. So I'm going to dissolve that into this. What was molality? Moles per kilogram, right? Well, 1 mole, they already did the calculation for me. Yeah, that's easy. Divided by, change the 250 to kilograms, and that's what? 0.25. Okay, so we're just going to plug that through. And we've got our molality. Molality, or the fancy little, well, that's a little bit too much. There we go. Little m. Okay? Now, I also wanted a percent of ethylene glycol by mass. So you need to do a little bit more. They gave me the mass, so I don't have to look it up. Yippee. Okay? So to do percent by mass, take this divided by total mass, times it by 100, I got percent, right?
Why are you saying grams instead of kilograms?
They have to be the same unit. When I do percent, it has to be in the same unit. So top and bottom have to be in the same unit.
So normally, if it was something like that, like ethylene glycol, would you get
They would give, I would give you the formula. So if they don't give you, like it is in here, grams is equal to this many moles, then you've got to know the formula. So if they say magnesium sulfate, I would expect you to know the formula of that, yes.
add the 2 zeros?
The 2 zeros here?
Yeah.
Yes, because I have 3 significant figures in the 250 and I have 3 significant figures in the mole. So I should have 3 significant figures when I end. Okay, going on. Maybe, blank page. Oh, and that's your learning check. I hope you got it
I
right.
think it's 3.
Yeah, I think it's 3 too. So let's just go over this really quickly. Okay, we want percent, so we're just going to take the 15 divided by 235 plus 15 and times it by 100.
Wait,
Okay.
oh, that's just to find the mass?
You're just in percent. You just want to find the percent.
No, so that was easy.
Yeah, that one's easy, right? Okay, so percent or ppm or ppb or pph, those are easy. Don't make them hard. They're just finding your percent. You gotta have the total on the bottom, whatever you're trying to find the percent of on the top, and times it by 100 or times it by whatever. Now, we're gonna go backwards. We're gonna go backwards here. So if I need to prepare, and they do this in the hospital all the time, the doctor will order percentage part by mass of sodium chloride or potassium chloride to go run through a patient's vein. You need to make it upright if you're a technician, right? So I want to end up with 10%. I want to end up with 10%. How did I get to percent? Well, I times something by 100. What did I times by 100?
Something over something plus 250.
Almost. He said that he needed to prepare 250, so that's a total amount. 250 and then just x, right? Because I already have the total amount. That's a 250 right here. But I don't know what added to make that 250, right? So now I just go down and I go x divided by 250 equals 0.1, right? And then I just times it over. X equals, what's 0.1 of 250? Our tenth of 250. 25. 25 grams. We're done. Whoops, sorry. 25 grams of NaCl. Yeah, I divided both sides by 100 to get to the 0.1. Okay? Oh, and it's going to come in anyway. All right. Okay, we're going to try this molal problem. So, 25 grams of NaCl is dissolved in 5,000 milliliters of water. Find the molality. Molality. Well, first of all, I need to know 1 gram is equal to 1 milliliter. Now you can do it. That's for water. That's something I will expect you to know. 1 gram is equal to 1 milliliter of water.
So to find
I didn't divide this one. This one I don't divide. This one I divide by 1,000. Because I want moles of sodium chloride and I want kilograms of the water. Remember, solute over solvent. So now I've got moles. What do I do now? Moles divided by kilograms. So I need to go forward here. There we go. So I just said, okay, 1 milliliter is equal to 1 gram, so 5,000 milliliters is equal to 5,000 grams. Therefore, if I divide that by 1,000, I got 5 kilograms. Everybody okay with that? Now take 0.4 divided by the 5. What is my molality? Come on, you guys can do this. 0.427 divided by 5. What is your molality? Okay. Not quite, but let's see, maybe. There we go. It's just not coming in. Okay, 0.0854 molality salt water. I'll pause that real quick. Okay, so with molality we can figure out what's called colligative properties. And adding a solute to a solvent, the properties of solvent are modified, and we do that a lot. Our vapor pressure decreases. That means the amount of water that we would lose from a saltwater solution would be less than the amount of water we'd lose to evaporation in just a glass sitting out with water. Okay? The melting point decreases. If I put salt on ice it lowers the melting point, and you say it melts the ice, but it really doesn't. It just lowers the melting point. Okay? It increases the boiling point, so if I put salt in my water and I go to boil noodles, it'll actually raise the temperature of the water a little bit higher and boil my noodles at a higher temperature so they don't go mushy. Osmotic pressure is possible. Because of colligative properties, my kidneys work. Without this, my kidneys would not work. Okay? All right, these are all called colligative properties, and you need to know the four and what they do. Are they increasing or decreasing or whatever? And we're actually going to be doing that. Now, these colligative properties and how much they affect something depend on the number of particles or the number of ions in a solution. So remember, any covalent compound is going to only have one particle floating around there. It's still going to affect my freezing point and my boiling point, but not as much as, say, salt that has 2, or magnesium sulfate that has 2, or calcium chloride that has 3, okay, or calcium phosphate that has 5, okay? So it depends on the ions. Now, here's pure water, here's ethylene glycol. Bet you don't know what that is. Good job, it is, it's antifreeze. That's one of the older versions of antifreeze. That's the one that they really worry about animals eating. Okay, this lowers the freezing point. So when I go out to start my car in the morning, it's not frozen. It'll actually start and work. My cooling system will work. Okay, have you ever gone out and got in your car and been driving in the fog? What happens to your headlights? Okay, it scatters all over the place. And the reason why is you've got a colloid. And the colloid has bigger particles than a solution, but not big enough to fall out. So they're big enough to catch light and scatter it, but not big enough to fall out of solution. So smoke and fog and clouds that are down lower, or even if you're in a forest, you can see the light coming through. That's because of what's called the Tyndall effect. Okay? All right, so changing freezing point. Why do we use it? Well, we use it for our cars. We use it to make ice cream, which we'll do next week. And we use it for getting ice off the road. All right, so common applications of freezing point. If you were using, if you were the city manager and you had to use one of these to keep the ice off the road, what do you think some things that you would consider would be? Okay, well, these are things you have at your disposal, but what are the things as a city manager you would worry about? Cost, right? Cost is a big one, right? You don't want to get fired because you got to keep the cost under. And you got to worry about what temperature is outside because these will melt ice, I'm doing quotations around the melt, ice at different temperatures. This only has, SiO2 has 1 particle. So it will lower it a little bit. So if it's not real cold outside, I use sand because it's cheap. If it's a little bit colder outside, I'll use NaCl, or regular rock salt, because it's next cheapest, but it lowers it twice as much as just sand does. So if it's colder outside. If it's really cold, then I've got to go to calcium chloride, which is expensive, but it'll keep my roads clean.
So rather than the freezing point being at 32, that would become a melting point technically?
Well, actually, we'll learn. When you make ice cream, it'll get down into the negatives. Okay, so we'll learn that when we do our ice cream lab. So common application is a boiling. Again, antifreeze. Because if it gets too hot, we don't want our cooling system boiling. That doesn't help cool. And making macaroni and cheese, of course, is one of the ones my kids liked a lot. This is the equation you need. Very, very important equation. Okay? You need to make sure you write that down because we're going to be using it a lot coming up. This is a freezing point or boiling point. You can use either one. It just changes the K. So if you're doing freezing point, it's Kf. If you're doing boiling point, it's Kb.
Is that like italic then?
Yeah, this is the italic M, the little, that's molality. K is a constant, and we'll talk about those in just a second. I is how many particles it will break into, and I think that's actually coming up here. It's called the Van Hoff factor. It's basically how many particles will it break into? How many ions? Okay? And delta T is a change in temperature. So, theoretical. If I have a compound glycol, how many I do you think it's going to break into? 1. Glycol is an organic. Okay, what about NaCl? 2. Okay, what about calcium chloride? 3. Yay! How about calcium phosphate? 5. Okay, so it's how many ions? It's how many ions it will break into. Okay, so everybody get that? You need to be able to do this to be able to do that equation up here. We're going to do some of that. Okay, now the ones that you need to be really worried about are this one and this one. Those are the ones you need to have memorized. This is KF, and this is KB for water. And those are the ones you need to know. Those are the ones we're going to be working with. Now, if we're going on to other classes higher up, we would fiddle with other things, but we're just going to worry about water. Okay? So this sort of explains it right here. M is molality, K is a molar freezing point. So depending on if I'm worried about the freezing point or worried about the boiling point, depends on which one I use. Okay? All right. So, and I highlighted them too. Okay. All right. Change in boiling point. So here we've got our thing. We've already figured out the molality. This is the same equation we just did earlier. What was the molality? Do you remember? Okay, it was 4. Okay, so since we're worried about boiling point here, we're going to use the 0.52. Okay, we already calculated the molality earlier. It was 4.0. So now we're going to find out how did that affect my boiling point. What's the boiling point of water? 200. In Celsius? 100. Okay, so we want to see how much higher, because it was boiling point elevation, that's going to make it, right? What? Probably. Okay, so we're going to use this right here as our I. We're using this as our molality, and because we've got glycol, which we decided earlier was 1 for the I, that's what we put in. So we just plugged everything in. Okay?
How do you figure out which one is the boiling and which one is the melting?
The one I gave you from the charts, the boiling was the 0.52 and the melting was the 1.86. Okay? All right, so then we get a number. That's the change in boiling point. Since it was boiling point elevation, meaning I'm adding it to 100, I add it to 100, I get my new boiling point. So this is my new boiling point of that solution.
That happens when you put glycol. So now it has to get hot.
Now it has to get that hot in order for it to boil.
What would you ever use that for?
Okay, when we do our glycol and our mix in our antifreeze, we have to have certain mixes in order to be able to raise the temperature or lower the temperature, depending on the weather. Okay? Pause it.
Can you record that for?
So I can put it up on the web, so if you want to re-listen to it, you can. And those that weren't here, that's where I can send them. Okay, so freezing point depression, what we're going to be using next week. Yay. Okay, we have got KF. This is KF now because I'm working with freezing point. I want to find out what the freezing point is of that 4.0 molal solution. I use the same equation. The delta T equals KMI, only this time I'm using KF for the freezing point. Plug in. Boop, boop, boop. Still have 1 as I. If I use salt, I'd use a 2 for I. If I use calcium chloride, I use a 3 for I. Okay? Get your number, plug it through. Now, freezing point depression. What's the freezing point of water? 0. So I'm depressing it even that much more. So I'm going to subtract it from 0, and I get the new freezing point. Now you notice it lowered the freezing point a lot more than it raised the boiling point, didn't it?
Is it easier to make it less?
So So we're going to be using this freezing point depression in order to freeze our ice cream. But we're not going to use glycol. We're just going to use salt.
Yeah, that might not.
Yeah, I don't think I would want to get there with glycol. Okay, so here's another one. Let's see what you can do with this one. See if you can figure this one out before I do. Okay? So what temperature will a 5.4 mol solution of NaCl, what's the I? 2, freeze at? Okay, plug in. Plug and chug.
How do you know what the F?
What's the freezing point of water? We're all just doing it in water.
Oh, okay.
1.86.
Use the 1.86, yes. So write down the equation and then just plug in.
I keep getting 0.
This is just this times this times this. 1.86 is the one number I had you circle under the KF. Okay, just plug it through. You get 20.1, subtract it from 0, and you got negative 20.1 as the new freezing point.
Should we do significant figures too? Because that one has 2 significant.
You have to be careful with significant figures on this because of adding and subtracting in here, but if you put 20, I would be okay because it had 2. Okay? So, to prepare a solution, weigh out the solid, dissolve it in the solvent. Remember I told you that earlier? So weigh out your solid, and then dissolve it into the solvent. And then we can dilute a solution. I get acids in like 18 molar or 12 molar. I don't put 18 molar or 12 molar out for you guys to use. It's really dangerous. There's very few times I let you use the really concentrated, and it's in small bottles, right? So I have to dilute it down. So we're going to learn what's called the dilution equation, which makes life really easy. So you want to make sure you have it down. M1 times V1 equals M2 times V2. Now what did I tell you we use most often in lab? What does that big M stand for? Molarity. Molarity, molitary. The molality is the fat one. Molality has to do with the colligative properties. So you got to keep those two. I know. I wish they would have chosen 2 different words. Okay, so where M1 is your initial molarity, V1 is your initial volume, M2 is your final molarity, and V2 is your final volume. So that's dilution. Okay, so this is what we're going to be practicing for the next couple week or 2. All right, so grab out your worksheet. I am going to help you for the first little bit, yep. If I can get this to go down. So I'm going to do one in each area for you so you can follow through. So we are calculating molarity for the first ones. So I'm just going moles divided by liters. So 2.3 moles divided by 0.54 liters. 45, sorry, dyslexic in my talk. Punch it through, and I get my answer in molarity of NaCl. What do we get? 5.1. Done. That's pretty easy, right? Moles divided by liters. Yep. Now, if you're not given liters, you got it like right here, you're not given liters, so you got to divide it by 1,000 before you do it. So it's got to be in moles and it's got to be in liters. So if you're given grams, you got to change it to moles. So let's go down to the next group here. Next group here, you're asked to find parts per million. What was parts per million? Do you remember?
10 to the 6.
Times 10 to the 6. So I'm going to take this 0.0120 grams divided by 2,400, 1234.012, because I had to add that on, right? Add them together. I just add that, times 10 to the 9 equals whatever ppm, 10 to the 6, thank you, it's million, of CaNO2. So what are we going to get when we times that through? right here. 0.05. Give me one more. We throw in a 0. Okay? Don't make it hard. This is easy stuff. Okay? Let's flip over to the back side. So I'm going to give you an example in each one. Okay, on this one, we're asked to find out how to make the solution. So I've got to find out how many grams to weigh out. So I've got molarity. I'm going to take the 6 molar, which is moles per liter, right? That's what big M stands for, right? And I'm going to times it by 2 liters. Liters are going to cancel out. I'll get 12 moles. Everybody okay so far? And it's 12 moles of HCl. So then I just convert it to moles. So in 1 mole of HCl, there is 36.4 458 grams of HCl. Yep, that's adding up a hydrogen and 1 chlorine. Then times that by 12, you got your answer. Grams HCl. Done.
How many significant figures?
1.
So really, you just times 6. You just times those 2.
I times those 2 so I can get moles. So I got to be careful though, if they don't give me liters, like right here, I got to change it to liters first.
So what about 4 grams?
So 400 grams, okay? Done. All right, the bottom one is also very simple. A lot of kids think it's very stressful, but it's not. How I got that last one? I'll go back up in just a second. Stay with me down here. I want to make sure we get through all of them. On this one right here, you're going to write the formula. So iron 2 phosphate. What does a 2 represent? Everybody keeps messing that up. The charge. So I'm going to write it over here. Fe has a +2 charge. What does phosphate have? Phosphate's PO4, -3. Okay, so I'm going to take that and I'm going to write the right thing right here. This is just sort of my practice area over here. So I'm going to have a total charge of what? 6. Okay, so how many Fe's do I need to make 6? 3. How many phosphate groups do I need to make 6? 2. Okay, this is a solid. When I'm doing a dissolution reaction, I go from my solid to my ions. How many ions did I say I needed of Fe? 3 Fe, and they were +2, and since they got an ion charge, they're a cute little ion. How many phosphates did I need? 2, so I put 2 PO4 has a -3 charge, and guess what? It's a cute little ion too. Doesn't really mean a cute little ion. What does it mean? Aqueous. It means dissolved in water. But that's an easy way to remember it. Okay, that's all you do. That's the answer to that one. That's it. Okay, yes?
Are they all?
If it has a charge, it's AQ. If it has a charge, it's AQ.